At the end of this video, you should be able to discuss the wave-particle nature of light. We discussed the wave nature of light in a previous video. In this video, we'll discuss the particle nature of light. So after this video, you should be able to do both. And then discuss the significance, not just tell me that it is significant, but tell me what it means, what it signifies. Discuss the significance of the photoelectric effect and the line emission spectrum of hydrogen to the development of this new atomic model towards which we are moving. The photoelectric effect. In the early 1900s, scientists conducted two experiments involving interactions of light and matter that could not be explained by the wave theory of light. One experiment involved a phenomenon known as the photoelectric effect. The photoelectric effect refers to the emission of electrons from a metal when light shines on that metal, as illustrated in figure 4-3. The mystery of the photoelectric effect involved the frequency of the light striking the metal. For a given metal, no electrons were emitted if the light's frequency was below a certain minimum, regardless of how long the light was shone. Light was known to be a form of energy, capable of knocking loose an electron from a metal. This was known, but the wave theory of light predicted that light of any frequency could supply enough energy to eject an electron. Scientists could not explain why the light had to be a minimum frequency in order for the photoelectric effect to occur. Moving on to light as a particle. The explanation of the photoelectric effect dates back to 1900, when German physicist Max Planck was studying the emission of light by hot objects. He proposed that a hot object does not emit electromagnetic energy continuously, as would be expected if the energy emitted were in the form of waves. Instead, Planck suggested that the object emits energy in small, specific amounts called quanta. A quantum is a minimum quantity of energy that can be lost or gained by an atom. Planck proposed that the following relationship between a quantum of energy, let me show you that definition one more time. A quantum is the minimum quantity of energy that can be lost or gained by an atom. Planck proposed that the following relationship between that quantum of energy and the frequency of radiation, as E is equal to h nu. In the equation, E is the energy in joules of a quantum of radiation. Nu is the frequency of the radiation emitted, and h is a fundamental physical constant now known as Planck's constant. H, Planck's constant, is equal to 6.626 times 10 to the negative 34th joule seconds. In 1905, Albert Einstein expanded on Planck's theory by introducing the radical idea that electromagnetic radiation has a dual wave particle nature. While light exhibits many wave-like particles, it can also be thought of as a stream of particles. Each particle of light carries a quantum of energy, and Einstein called these particles the smallest unit possible to lose or gain by an atom. Those smallest units, he called them photons. A photon is a particle of electromagnetic radiation having zero rest mass and carrying a quantum of energy. The energy of a particular photon depends on the frequency of radiation, as per Planck's equation. So the energy of a photon is equal to h multiplied by the frequency of that photon. Einstein explained the photoelectric effect by proposing that electromagnetic radiation is absorbed by matter only in whole numbers of photons. In order for an electron to be ejected from a metal surface, the electron must be struck by a single photon possessing at least the minimum energy required to knock the electron loose. According to the equation, E of the photon is equal to h nu. This minimum energy corresponds to a minimum frequency. If a photon's frequency is below the minimum, then the electron remains bound to the metal surface. Electrons in different metals are bound more or less tightly, so different metals require different minimum frequencies to exhibit the photoelectric effect. Moving on to the hydrogen atom line emission spectrum. Now, when current is passed through a gas at low pressure, the potential energy of some of the gas atoms increases. The lowest energy state of an atom is its ground state. A state in which an atom has a higher potential energy than it has in its ground state is an excited state. When an excited atom returns to its ground state, it gives off the energy it gained in the form of electromagnetic radiation. The production of colored light in neon signs is a familiar example of this process. Now, when investigators passed electric current through a vacuum tube containing hydrogen gas at low pressure, they observed the emission of a characteristic pink glow. And you'll see that glow right here in figure 4-5. When a narrow beam of emitted light was shone through a prism, it was separated into a series of specific frequencies, and referring back to C is equal to lambda nu, therefore specific wavelengths of visible light. The bands of light were part of what is now known as hydrogen's line emission spectrum. And again, the production of hydrogen's line emission spectrum is illustrated in figure 4-5. Classical theory predicted that the hydrogen atoms would be excited by whatever amount of energy was added to them. Scientists had thus expected to observe the emission of a continuous series of electromagnetic radiation. Why had the hydrogen atoms given off only specific frequencies of light? Attempts to explain this observation led to an entirely new theory of the atom called quantum theory. Whenever an excited hydrogen atom falls back from an excited state to its ground state or to a lower energy state, it emits a photon of radiation. The energy of this photon, which we've already defined as E of the photon is equal to h nu, is equal to the difference in energy between the atom's initial state and its final state, as you can see by referring to figure 4-6 on page 95 of your textbook. The fact that the hydrogen atoms emit only specific frequencies of light indicated that the energy differences between the atoms' energy states were fixed, meaning non-changeable. This suggested that the electron of a hydrogen atom exists only at very specific energy states. Additional series of lines were discovered in the ultraviolet and infrared regions of the hydrogen line emission spectrum. The wavelengths of some of the spectral lines are also shown in figure 4-7, also on page 95 of your textbook. They are known as the Lyman, Balmer, and Paschen series, named after their discoverers. In the late 19th century, a mathematical relationship that related the various wavelengths of the hydrogen line emission spectrum was developed. The challenge facing scientists was to provide a model of the hydrogen atom that accounted for this relationship. So after this video, now you should be able to discuss the dual wave particle nature of light and discuss the significance of the photoelectric effect and the line emission spectrum of hydrogen to the development of the atomic model. Now moving into the quantum model.